For the last few lectures, we have been talking about Lyapunov's stability theorem, which we said is quite a powerful method, quite a powerful tool to determine the stability of an equilibrium point for a given nonlinear autonomous system. Okay. And the method went as follows. What you do is you pick a positive definite function. Usually, if you have some intuition, some physical intuition about the system, you have some obvious candidates, like for a mechanical system, you go with the total energy of the assembly. Okay, and then with that Lyapunov function candidate, a positive definite function, what you do is you try to figure out the behavior of that function, that scalar function, along the solutions of the system. Okay, and to understand that qualitative behavior, what you do is you compute the time derivative of your Lyapunov function, which simply is the inner product of the gradient of the Lyapunov function with the right-hand side of the system, f of x. Okay. So, having started with a positive definite function, you compute its time derivative v dot, and you look at v dot. Okay. If v dot is negative semi-definite, okay, so it's never positive, then it means that your equilibrium point, without the subgeometry, we take it to be the origin. The origin is stable. Okay, it's a stable equilibrium point. If v dot is negative definite, okay, that is, if it's always negative except at the origin, then the origin is asymptotically stable. Okay, so that's when things go smoothly. Suppose that you start with the Lyapunov function candidate, positive definite function, then you computed its time derivative v dot. And the result is that it's neither negative semi-definite nor, let's say, positive semi-definite. It's nothing, it's indefinite, okay? Now, what's the conclusion then? Well, the Lyapunov's stability theorem tells us nothing, therefore, there's no conclusion for such a case. So what you do then is you go back to step one and choose a different Lyapunov function, for instance, okay? And then for that, compute v dot, its time derivative, and check whether it's negative semi-definite or not. Okay, suppose that you continue this process a couple of times, and then all the time v dot turned out to be indefinite. Okay, so all the time the procedure turned out to be inconclusive. Then you start asking yourself, maybe there is no such Lyapunov function. Okay, that means maybe the origin whose stability I'm trying to establish is not stable to begin with. Okay, so in that case, it's good to know for sure that the origin is unstable. Okay, and how you do that? Well, usually to prove instability or stability, also what you do is you go to linearization method, but it doesn't work always. Okay, sometimes linearization method is also inconclusive. So in such cases where you want to show a suspected instability of the origin, here is the tool that is most general. Okay, it's again by a Russian scientist. It's called, I don't know how to pronounce it properly. I'm going to call it Chitaev. Okay, Chitaev instability theorem. Okay. So with Lyapunov theorem, we establish stability or asymptotic stability. With Chitaev's theorem, what we do is we establish instability of the origin. Okay. It's quite straightforward, the statement of the theorem. Its proof is also straightforward. Although we're not going to go through the proof, I advise you to, or I encourage you to go to the text and read it. It's quite short and quite understandable. Okay. So, consider the autonomous system x equals f of x with origin being an equilibrium point with f0 being 0. And then suppose you were able to find a function, a scalar function, okay, that maps points from Rn, and Rn is where our state resides. Okay, so we talk about an n-dimensional system. Rn, or it satisfies some continuity properties, continuously differentiable, and it's 0 at 0. Okay, but unlike the Lecture12 theorem, we're not going to require this function to be positive definite. Okay, we're not going to require indefiniteness condition on our function v. Okay, now let us construct the following set. Let u be x in Rn, and u of x is strictly positive. Okay, so this is the set of all points for which this function takes a positive value. Okay, that we're calling u. And then furthermore, suppose the following conditions hold. Okay, 1. There exists some positive number, it could be small, such that b dot x, and by b dot we mean the gradient, the inner product of the gradient of v with the right hand side of the system f of x. V dot of x is strictly positive for all x that belongs to the intersection of u, defined here instead of positive v's, and x in Rn, x is not equal to r. Okay, so this set is the set of all points that are in our within our ball. Okay, that the equivalences is no greater than r, and also they belong to the set U where v takes positive values only. Okay. So that's the first condition. Second condition is that U has points arbitrarily close to the origin. Okay, that means you cannot find a ball around the origin such that that ball doesn't touch this set U. Okay, no matter how small that ball is. Okay, that is for each epsilon there exists a point in U, x in U, with x less than or equal to epsilon. Okay. Now, if these two conditions are satisfied, then the origin cannot be stable. The origin is unstable. Okay. Now let's try to, instead of proving this, let's try to understand why these conditions give us instability over a simple example. Okay, and an example is from the textbook. show the instability of the origin for the system that I will put down soon enough. But let's first get familiar with the function that we'll be working with, v of x. Okay? So this is a second order system, and v of x is defined as x1 squared minus x2 squared. Okay? So clearly, this v is neither positive definite nor negative definite, okay, or semi-definite. It's an indefinite function. It takes positive and negative values, okay, for different state or different x. Now with that, v is indefinite. Okay. Now let's try to figure out the regions where v is positive and where v is negative. So for that, what we do is we mark these lines passing from the origin with 45 degrees and 135 degrees. Angles. Okay. So this is the x1 equals x2 line, and here this is x1 plus x2 equals 0 line, or x1 equals minus x2 line. Okay. Now, on those lines, when the magnitudes of x1 and x2 are equal to one another, this v is 0. Okay. And here, where the magnitude of x1 is larger than x2, v is positive. Likewise, here v is positive, and on the remaining wedges, the v is negative. Okay. So here, what we're interested in, where v is positive, and here, where the v is positive. Okay. So therefore, this is what we're calling u. Okay. The set of points where v is positive. U where v of x is positive. Okay. And here and here, v of x equals 0. Okay. So here we're positive, and then if you move in that direction, we become 0, and then we pass to the v less than 0 region, or v negative region. And this is the origin. Now, for this, well, this function we will use in Chetaev's instability theorem for the following system. Consider system or a family of systems which is given as x1 dot equals x1 plus g1 of x and x2 dot equals minus x2 plus g2 of x. X is the state vector, x1, x2. With functions g1 and g2 satisfying gi of x less than or equal to some positive constant times the norm square of x. Okay? I equals 1, 2 in sum. Neighborhood of the origin, d of the origin. Okay. note that this inequality guarantees that at x equals 0 for x the origin, this thing, okay, less or equal to 0. Okay, and that means that the origin is an equilibrium point. Okay. Note that. Right. Plug in x equals 0. Okay. The magnitude should be less than or equal to 0. If magnitude is 0, therefore the thing itself is 0. That means both G1 and G2 at the origin must be 0. And that automatically gives us that the origin is an equilibrium point. Okay. So note that. Gi must be 0 according to this condition, and x equals 0 therefore is equilibrium for the system. Okay, now let's show that this equilibrium, the origin, is unstable through Chetaev's instability theorem and employing that function given b of x. Okay, so for that what we do is we compute the time derivative of v. Okay. So let's do that. V dot of x equals the gradient, and then you take inner product with the right hand side, okay, which reads, okay, x1 minus x2. So x1 minus x2 vector is the gradient of v. Okay. So take its transpose, it becomes this row vector, and then we're taking multiplying with the right hand side, x1 plus g1 of x and minus x2 plus g2 of x. That reads x1 squared plus x2 squared plus x1 g1x minus x2 g2 of x. Okay, and now let's try to find some region where this v dot is positive. For x in D, suppose that we're in this neighborhood D of the origin, and within that neighborhood, the condition that the norm or the absolute value of Gix is bounded by the norm square of the state. Okay, for x in D, we can write the following. V dot of x, okay, that we computed to equal plus x1 g1 of x minus x2 g2 of x. Okay, so that's greater or equal to x1 squared plus x2 squared minus x1 times g1 of x minus x2 times g2 of x norm. Okay. So this could be either positive or negative. Likewise, this could be either positive or negative. But then what we do is we take this is always positive and this is always positive, and then we put minus signs in front. Therefore, the term here that we wrote down is always smaller than the v dot. Okay, so v dot can always be lower bounded by this. Now let's continue manipulating the terms over there. That's greater than or equal to what? This is the norm square of x. Okay, x squared minus norm of x. Note that x1 or the absolute value of x1 is always or never greater than the norm of x, therefore minus absolute value is always greater than or equal to minus the norm of x times g1 of x. And then we can do the same trick over there times g2 of x. Okay. So let's reorganize the terms. Minus norm of x times g1 of x plus g2 of x absolute value. Okay. That's greater than or equal to norm of x squared minus norm of x times. Because we are in this neighborhood, we can use this inequality and upper bound those two things. Okay. And we have therefore 2k norm of x squared. Okay. And that we can write as squared times 1 minus 2k norm of x. Okay. So what we want is we want to obtain a region where v dot is positive, and that region can be chosen by assuming that this norm of x is small enough. If norm of x is small enough here, then such that it's 2k times norm of x is smaller than 1, then these things become positive, and then v dot is larger than something positive, therefore v dot must itself be positive. And what's that set where v dot is positive? It's the following. Now, choose R. Okay, that's the R that we're going to use. That's been used in the statement of the instability theorem. That belongs to the following integral. Okay, so greater than 0 but less than 1 over 4k. Such that dr, which is the R ball is within the neighborhood of D. Okay. So we want R both to be smaller than 1 over 4k, okay, and so that this is greater than 1/2, 1 minus that. But also we want R to be small enough so that we are within the neighborhood D. Because if we are outside neighborhood D, then we cannot use this inequality, and then what we have obtained would be invalid, because from this line to this line we use that inequality, okay, to obtain this lower bound on beta. Okay, now we're ready to make the final conclusion. Then for x that belongs to U intersected with the R ball, we have v dot of x greater than or equal to, okay, so this is R is smaller than 1 over 4k, and then plug in 1 over 4k here, it gives you something less than 1/2. Therefore, this thing is greater than 1/2 times norm square of x. Okay, that of x greater than 1/2 norm of x squared. And clearly, this is positive. Okay, provide that we are in this set. Hence, by the previous theorem, times is unstable. Okay. That is, we can never find. Now remember the definition of stability or instability. We can never find delta small enough such that if we start within delta neighborhood of the origin, we will remain for all times within epsilon ball, but in this case epsilon is r. Okay. For all t greater than equal to 0. Okay. And the reasoning is pretty straightforward. Okay, so this was here and here were the places where V is positive. Okay, and then we take an intersection of that region with the R ball. Okay, and then so what we're talking about is we're talking about this side here. Okay, this is the origin. X1 and X2. This is R, this is minus R. Okay, remember that on these lines, V is 0. And now in this region, V is positive. Now, you start anywhere on that region, okay, and you can choose a point that's arbitrarily close to the origin. Okay, so what's going to happen is, in this region, V dot is positive. Okay, V dot positive means that V is increasing. Okay. Now, V is increasing, and while that's the case, it cannot stay forever in this bounded region. Okay, why is that? Because since V is increasing, since V dot is positive, so V is increasing forever. Okay, if it stayed in this region forever, but it cannot stay in this region forever because eventually V has to get unbounded and has to move away from the origin, okay, arbitrarily far. Okay, so at some point, therefore, since V is positive, V dot is positive here, V or the solution should get out of this set. Okay, now the solution cannot get out of this set from this line here because V is 0, and we start with some positive V, and V dot is positive. Therefore, in order to leave this set from this line, we have to, from positive V, we have to go to a 0 V. Okay, so that means at some point V dot has to be negative, the slope has to be negative, but V dot is always positive in this region. Therefore, we cannot leave this region from this line. Likewise, we cannot leave the region from that line too, where V is 0 and V is 0 here. Therefore, there's only one exit that we can leave the set, and we have to leave the set at some point, and that exit is this R. Okay. At some point, we have to leave the set. Okay, from this border, and leaving the set from this border means that the norm of solution has to hit R at some point. So no matter how close to start the origin, eventually you have to reach a point where the norm is R, and using that observation, the stability breaks down from the very definition of stability. Okay. And in our next example, we will return to, once again, to Lecture's theorem and apply it to a very practical problem. Euler equations for a rotating rigid spacecraft. Okay. So we're now going to apply Lecture12 theorem to a rigid body. Okay. The equations are so-called Euler's equations. Okay. J2 minus J3 omega 2 omega 3 plus torque U1. And J2 omega 2 dot equals J3 minus J1 omega 3 omega 1 plus torque, second torque, and J3 omega 3 dot equals J1 minus J2 omega 1 omega 2 plus third torque. Okay. Now here omegas, they are the angular velocities. Omega 2, omega 3. Components of the angular velocity vector. Omega R3 along the principal axis. So those are angular velocities, and J's are constant scalars. They are principal moments of inertia. Okay. Positive constants. And finally, U's are torques. Torque equals. Now, for the system, we consider the torque-free case and also the case with torques. And we'll try to establish spherical stability and stability. In part A, we are asked the following case. Consider the torque-free case. That is, all torques are set to 0, UI equals 0. Show that, for that case, the origin is stable. Omega equals 0 is stable. And in part B, we will consider the system under feedback. UI equals minus Ki omega I with K1, K2, K3 being positive constants. Show that for that case, the origin has to be globally asymptotically stable. Okay. Now, let's start dealing with the problem from the point of view of Lecture12 stability theorem. So for that, what we need is a Lecture12 function. A Lecture12 function this is a physical system, okay, a mechanical system. Therefore, let's go with something that has some physical meaning. For instance, the energy, okay, of the system. And what's the energy? Energy for the system is given as 1/2 omega transpose J omega. No, that is a generalization, or analogous to the case 1/2 m times v squared for a mass that moves on a straight line. Okay, and then m is replaced by this inertia matrix, and the velocity is replaced by this angular velocity. Of course, this is a vector, and then omega squared doesn't make sense. So what we're dealing with, we construct this sort of generalized inner product. Okay, omega transpose J omega. Okay. Now, in open form, this reads 1/2 J1 omega 1 squared plus 1/2 J2 omega 2 squared plus 1/2 J3 omega 3 squared. Okay, so that's the total energy of the rotating body. And let's, by the way, here J is a diagonal matrix with non-zero entries being J1, J2, and J3. Diagonal J1, J2, J3 is defined to be J, which is a 3×3 matrix. Okay. Now this is our Lyapunov function candidate. Clearly, it's post-definite. Okay. And therefore, we can use it to check stability. And to do that, what we do is we have to compute its time derivative. Okay, we have to compute E dot. So E dot omega is J omega 1 dot plus J1. J2 omega 2 dot plus J3 omega 3 dot. This is E, and then its time derivative. It's clearly what's written over there. And then what we're going to do is we're going to pull V1 dot V2, omega 1 dot omega 2 dot omega 3 dot from the system equations. Let's do that. Okay, so that equals omega 1 times J1 omega 1 dot. J1 omega 1 dot is J2 minus J3 omega 2 omega 3. Okay. Plus omega 2 times J2 omega 2 dot, which is J3 minus J1 omega 3 omega 1, and finally plus omega 3 times J3 omega 3 dot, which is J1 minus J2 omega 1 omega 2. Okay. Now, for each term we have omega 1 times omega 2 times omega 3. Okay, so we take into the count parentheses J2 minus J3 plus J3 minus J1 plus J1 minus J2, and everything is multiplied by omega 1, omega 2, omega 3 product. Now, here a very nice thing happens. Ej is cancelled, J2 with minus J2 and minus J3 with J3. Okay. And regardless of omega values, therefore E dot is always 0. So which is sort of expected. This is a lossless system without any disturbance from the outside, because we let all the torques to equal 0 because in the torque-free case, and we have therefore E dot equals 0. This means, not surprisingly, energy is conserved. And what's the implication of that energy is conserved from the stability point of view? It's obvious. Energy conserved means that this thing is constant, it's a positive function for Laminar solutions of the system, and therefore, if you start close to the origin, you always remain close to the origin. As a result, the system is, or excuse me, the origin is stable, okay, by Lyapunov's theorem. Conclusion. E dot is never positive, therefore E dot is negative semi-definite, and by Lyapunov's theorem the origin is stable. Okay. Now in general, with a negative semi-definite derivative of Lyapunov function, we cannot say anything about asymptotic stability, okay, in general. But here it's a very special type of negative semi-definiteness. It's exactly zero, okay? It's not sometimes zero, sometimes negative, it's always zero. So that means E is constant. And if E is constant, it means that the state cannot be converging to the origin, okay? Because state converging to the origin would mean that E has to converge to zero also, but E is not converging anywhere, it's constant. Therefore, we can be sure that the system, the origin is not asymptotically stable. E dot exactly equals zero implies that E of omega t is constant. Okay. So energy at all future times equals the initial energy. And as a result, omega of t cannot be converging to the origin, and therefore the origin cannot be asymptotically stable. Okay. Now, some of you may point out that, well, energy is conserved, and that's what we expect, but there are other things that are conserved also. For instance, the angular momentum. What happens, or what would have happened if we had worked with the angular momentum instead of the energy? Okay. So let's see that. It's an interesting question. There's another conserved quantity, that's angular momentum. So let's use that, or norm square of that, as Lyapunov function candidate. How about the angular momentum? Okay, let's call it M. Yeah. I'm going to give the definition of norm square of angular momentum as follows: J omega norm square. Okay, J is our inertia matrix and omega is our angular velocity vector. And this thing can be written as omega transpose J square omega. Okay. Now, the form looks similar to the energy, but it's different in the sense that in the energy we had 1/2. Well, that 1/2 is not that important. We had omega transpose J omega. And then if you square the matrix in between, what you obtain is you obtain the angular momentum, or the norm square of angular momentum. Okay. Clearly this too is a positive definite function, and let's see what happens if you use it as a Lyapunov function candidate. Okay. And this can be written as J1 square omega 1 square plus J2 square omega 2 square plus J3 square omega 3 square. Let's compute the time derivative of the momentum square omega t. Okay, equals 2J1 square omega 1 dot plus 2J2 square omega 2 dot plus 2J3 square omega 3 dot. And now dots will be coming from the system equation, which we were given. And let's do that. 2J1 omega 1 times J1 omega 1 dot, and which is here. 2 minus J3 omega 2 omega 3. Okay. Plus 2J2 omega 2 times omega 2 J2 omega 2 that, which is J3 minus J1 omega 3 omega 1. Finally, 2J3 omega 3 times J3 omega 3 dot, which is J1 minus J2 omega 1 omega 2. Okay, so it looks quite a mess, but there will be a very beautiful cancellation, and again, you will reach the conclusion that we were expecting to reach. Okay, 2 times J1, J2 minus J3 plus J2 J3 minus J1 plus J3 J1 minus J2 times omega 1 omega 2 omega 3. Okay. And again, if you look at the terms here, you will see a cancellation. So look at that, and we have once again we have no function's derivative equal to 0. And this means that momentum is conserved. Okay. Now this has very important consequences, this being both energy and momentum, or both of those positive functions being or having zero derivatives, has a very important geometrical consequence, which is very easy and pleasant to visualize. Okay, so let's do that, and then we can finally talk about very briefly part B, where we have talks. Okay, here is the conclusion. Both the energy and angular momentum are conserved. Okay. Hence, each solution, each trajectory of the system omega t must traverse the intersection of two separate Lyapunov surfaces belonging to two separate Lyapunov functions. Two Lyapunov surfaces. Okay. That is, omega t must at all times, the solution must at all times belong to the intersection of this omega in R cube, such that E of omega equals E of omega initial. Okay. And this we are intersecting with omega in R cube n squared omega equals n squared omega 0. Okay. And what's the visual conclusion or visual implication of that intersection? It's the following. It's not that easy to draw, but this is sort of an ellipsoid. This also is another ellipsoid. Okay, and then we're talking about the intersection of an ellipsoid with another ellipsoid. Suppose for simplicity one of those ellipsoids is a sphere, perfect sphere. Okay, and then we're talking about intersection of an American football with a basketball. Okay, And that could be roughly be visualized as the following. Suppose that this is our three-dimensional state space, omega 1, omega 2, and this is omega 3. This omega 3 is perpendicular to the plane spanned by this omega 1 and omega 2 axis. Here this is the origin. And then we have the American football. Something like this, let's say. And this is where this is the sort of the equator. Here, this is the other equator. Okay. And then, what you do is you take a ball, a sphere, and cut it. Look at the intersection. And then you take a larger sphere, look at the intersection. And if you mark those intersecting points, you will see something like this. Excuse my bad drawing. Something like that. Okay. So that means if you start somewhere here initially, then you will always remain on that curve that you obtain by intersecting the constant energy surface with the constant angular momentum surface. So you traverse a funny three-dimensional, funny curve, funny loop, but it's a closed loop as you go on in time. Okay, so that also means since that curve is closed, okay, so it's a loop, that means the solution must be periodic. Okay, even though this is not a second order but a third order system. Okay, so that's what we can say for the torque-free case. Now let's very quickly talk about when we have the torques chosen as negative feedbacks. Okay, UI equals minus Ki omega I Ks. Okay, Ks are positive. When you apply such torques, you have this time we have E dot omega equals minus K1 omega 1 squared minus K2 omega 2 squared minus K3 omega 3 squared. Since K's are positive, clearly this is a negative definite time derivative. Okay, and that means by Lecture's theorem that the origin is associated with state. E dot omega is negative definite. Throughout RQ. That means omega equals 0 is asymptotically stable. In fact, we can say more than that, because the Lyapunov function, the energy is radially unbounded. The sphere stability is global. So omega equals 0, the origin is globally asymptotically stable.